Welcome back to our channel. Today we explore the hidden secrets of nature. Omni Eyes presents episode 57, Exploring Caterpillar Vision. Do not underestimate the humble caterpillar. While it crawls slowly, its unique visual system holds incredible secrets for modern computer science. Unlike humans, caterpillars do not see the world in sharp detail. They rely on tiny black spots called stomata for survival. These simple eyes are positioned carefully on the sides of their heads, offering a very different perspective of the surrounding environment. They do not possess complex lenses or retinas. Instead, they operate like extremely basic light sensors, capturing the absolute bare minimum. Imagine looking through a heavily pixelated filter. That is exactly how a caterpillar perceives its vibrant, green, and highly dangerous world. To them, a beautiful blooming flower is merely a blurry patch of brightness against a dark, undefined, and constantly shifting background. Why would nature design such an apparently flawed system? Because in the wild, survival often depends entirely on pure processing speed. A caterpillar does not need to admire the intricate patterns on a leaf. It only needs to know if danger approaches. When a predatory bird swoops down, the caterpillar does not analyze the feather details. It simply detects a fast, looming shadow. This sudden change in light and dark triggers an immediate defensive reaction, saving the tiny creature from becoming a quick meal. This remarkable biological mechanism is exactly what we call low-resolution motion tracking in the rapidly advancing artificial intelligence field today. In modern technology, we often obsess over ultra-high definition. We believe that 4K resolution is always the best solution. However, processing millions of pixels every single fraction of a second requires massive computational power, heavy batteries, and extremely expensive hardware. If an artificial intelligence system needs to react instantly, forcing it to analyze huge video streams will only cause dangerous delays. This is where engineers look back at the caterpillar. They realize that simplicity is often the ultimate key to incredible speed. By intentionally reducing the camera resolution, we allow the computer processor to focus entirely on detecting movement instead of rendering details. Just like the stomata, a smart security camera does not need to see the exact fabric texture of an intruder jacket. It only needs to recognize that a large, human-shaped mass of pixels is moving rapidly across a restricted, secure area. Once the system detects this fundamental movement, it can immediately trigger alarms, lock doors, or alert the authorities without any hesitation. This lightweight approach is revolutionizing how we design autonomous drones, robotic vacuum cleaners, and advanced industrial monitoring systems across the globe. Drones flying through dense forests use low-resolution sensors to dodge branches quickly, perfectly mimicking the caterpillar's rapid response to sudden obstacles. The less data the drone has to process, the faster its artificial brain can send steering commands to its spinning propellers. Let us dive deeper into the anatomy of the caterpillar's stomata to understand exactly how this biological marvel captures incoming light. Usually arranged in a small semicircle, these 6 tiny dots work together to provide a rudimentary panoramic view of the world. Each individual stemma acts like a single pixel in a digital camera, registering only basic information about light intensity and color. When an object moves across their field of view, the shadow passes from one stemma to the next in rapid succession. The caterpillar tiny brain calculates the time difference between these light changes to determine the speed and direction of the incoming threat. It is a masterclass in minimalist engineering. Nature has stripped away all unnecessary visual information to achieve maximum efficiency and survival. Computer scientists use a very similar technique called optical flow to teach robots how to navigate through unpredictable and dynamic environments. Optical flow algorithms track how pixels move between consecutive frames, allowing machines to estimate the relative motion of surrounding physical objects. If we feed these algorithms high-resolution images, the math becomes overwhelmingly complex, causing the robot reaction time to drop significantly. But if we compress the image into a low-resolution grid, the robot can calculate optical flow almost instantaneously and avoid collisions. This proves that having more data is not always advantageous. Sometimes, filtering out the noise is the smartest thing to do. Think about a self-driving car driving through a heavy rainstorm. High-definition cameras might get confused by falling water droplets. A low-resolution sensor, however, will completely ignore the tiny raindrops and focus only on the large, solid shape of another vehicle. By adopting the Caterpillar philosophy, automotive engineers can build safer, more reliable autonomous driving systems that perform well under harsh conditions. The concept of low-resolution vision also plays a crucial role in edge computing, a rapidly growing trend in modern tech architecture. Edge computing means processing data directly on the device itself, rather than sending it all the way to a distant cloud. Sending 4K video streams to the cloud requires massive internet bandwidth, which is not always available in remote or rural locations. A lightweight, low-resolution sensor can process movement locally, triggering an alert using only a tiny fraction of the standard network bandwidth. This makes smart agriculture possible. Farmers can deploy thousands of cheap, low-power sensors to monitor their massive crop fields for pests. These sensors do not take beautiful photographs. They simply watch for the telltale low-resolution movement patterns of invading insects or animals. It is incredibly poetic that we are using technology inspired by the caterpillar to protect our crops from actual hungry green caterpillars. Let us take a moment to appreciate the incredible journey of evolution that led to the development of these fascinating biological stomata. Millions of years of natural selection have perfectly tuned this visual system to match the exact needs of a crawling insect. A caterpillar spends most of its life eating leaves, growing rapidly, and trying desperately to avoid becoming bird food before its metamorphosis. It does not need to hunt fast-moving prey, nor does it need to recognize the faces of other caterpillars around it. Therefore, investing biological energy into developing complex, high-definition eyes would be a complete and utter waste of limited physical body resources. Nature is the ultimate optimizer. It never builds a supercomputer when a simple, elegant calculator can easily do the exact same job. We can apply this exact same evolutionary logic to the way we design and build artificial neural networks in modern computer science. Many modern AI models are bloated, requiring massive server farms and consuming terrifying amounts of electricity just to perform basic fundamental tasks. Researchers are now actively trying to shrink these massive models down, creating tiny AI systems that run perfectly on standard battery power. By intentionally reducing the precision of the data, these tiny models can run significantly faster while consuming almost zero external electrical energy. This process is known as quantization. It is the artificial intelligence equivalent of seeing the world through a heavily pixelated, simple caterpillar eye. Quantized neural networks are currently powering voice assistants in smartwatches, health monitors, and predictive maintenance sensors inside heavy industrial manufacturing plant facilities. They prove that you do not need absolute perfection to achieve highly useful, reliable, and practical results in the demanding real world. Let us return to the forest canopy. A caterpillar is slowly inching its way along a bright green, beautiful sunlit oak leaf. Suddenly, a large wasp hovers nearby. Wasps are terrifying predators that lay their parasitic eggs inside the bodies of unfortunate green caterpillars. The caterpillar cannot see the wasp's yellow stripes. It only registers a dark, blurry blob oscillating wildly in its extreme peripheral vision. That simple, low-resolution visual cue is more than enough. The caterpillar instantly drops from the leaf, hanging safely by a silk thread. This instant escape mechanism is a flawless demonstration of how raw processing speed easily beats high-resolution clarity in extreme survival situations. Imagine a military defense system designed to intercept incoming missiles. It cannot afford to waste precious milliseconds rendering beautiful graphical computer interfaces. It relies on raw radar data, tracking blurry, low-resolution blips on a screen to calculate trajectories and launch immediate defensive countermeasures. Whether it is a tiny insect in the jungle or a billion-dollar defense grid, the fundamental principles of survival remain identical. Identify the threat quickly. Ignore all the irrelevant background details. React immediately before it is completely too late to save yourself entirely. The study of animal vision continues to inspire countless breakthroughs in the fields of robotics, computer vision, and fully automated machine learning. Beyond caterpillars, scientists also study the compound eyes of flies and the incredibly complex polarization vision of mantis shrimp for biological inspiration. However, the caterpillar remains the absolute best example of extreme minimalism, constantly teaching us how to do so much with so little. As we move towards a future filled with smart devices, we must remember the valuable lessons taught by this humble, crawling creature. We cannot simply put a high-definition, power-hungry camera on every single object in our homes, streets, and massive industrial production facilities. Privacy is another major concern. High-definition cameras constantly record faces, license plates, and sensitive personal details, raising severe ethical security questions. Low-resolution sensors solve this privacy problem beautifully. They can monitor a public space for unusual activity without ever identifying individual people. A smart building can use these sensors to count how many people are in a room and adjust the air conditioning accordingly. Because the resolution is so incredibly low, nobody's privacy is violated, yet the building still operates with maximum energy efficiency perfectly every time. This is the magic of low-resolution motion tracking. It provides essential situational awareness while inherently protecting our fundamental right to human privacy. It is fascinating how a biological adaptation meant to save an insect from birds can help humans build safer, more ethical modern cities. The next time you see a green caterpillar munching on a leaf in your garden, take a moment to look closely at its head. Notice the tiny black dots, the stomata, quietly processing the world in a way that modern engineers are desperately trying to perfectly copy. It is a living, breathing masterclass in data optimization, crawling slowly across a branch, completely unaware of its own incredible technological brilliance. Let us explore how software developers actually code these low-resolution motion tracking algorithms using modern programming languages and advanced machine learning. First, the software converts the incoming video feed into a simple grayscale matrix, completely removing all unnecessary color data to save valuable memory. Next, it drastically reduces the resolution, turning a sharp image into a highly pixelated grid of simple light and dark geometric squares. The algorithm then compares the current grid to the previous one, looking for any squares that have significantly changed their overall brightness. These changing squares indicate movement. The software groups them together, drawing a simple bounding box around the newly detected moving object immediately. This entire calculation takes only a few milliseconds, allowing the system to track objects in real time on incredibly cheap silicon computer chips. This is the exact same mathematical logic that the caterpillar nervous system executes biologically when a shadow falls across its tiny stomata. Biology and computer science are two sides of the exact same coin, constantly searching for the absolute most efficient solutions to complex problems. While humans invent silicon chips and complex software codes, nature uses proteins, neurons, and millions of years of brutal evolutionary testing. Sometimes nature's solutions are so elegant and simple that they completely revolutionize the way we approach complex engineering and modern design challenges. The concept of low-resolution vision reminds us that we should always define the actual problem before we build a highly complicated solution. If the goal is simply to detect movement, you absolutely do not need an expensive 4K camera and a massive supercomputer. You just need a few basic sensors and a clever algorithm, just like the 6 tiny stomata on a small green caterpillar head. This philosophy of minimalism is spreading rapidly across the entire tech industry, inspiring a new generation of highly efficient, sustainable smart devices. We are learning to build technology that works smarter, not harder, by embracing the brilliant simplicity found deeply within the natural world. As we conclude today's fascinating journey, let us summarize the incredible lessons we have learned from the humble, slow-moving green caterpillar. We discovered that their simple eyes, known as stomata, provide a heavily pixelated but highly effective view of their dangerous natural surroundings. We learned that this low-resolution vision is actually a massive evolutionary advantage, allowing them to detect predatory motion almost instantaneously today. We explored how this biological concept directly mirrors the low-resolution motion tracking algorithms used in modern artificial intelligence and smart security systems. We saw how reducing data complexity leads to faster processing speeds, lower power consumption, and highly robust edge computing applications worldwide. Most importantly, we realized that bigger and more complex is not always better when it comes to solving real-world engineering problems. The caterpillar proves that true elegance lies in absolute simplicity, achieving exactly what is necessary without wasting any precious biological resources. Nature will always be our greatest teacher, offering endless inspiration for those willing to look closely at its beautifully optimized biological designs. Thank you for joining us on this deep dive into biology and artificial intelligence. We hope you enjoyed this fascinating scientific exploration. If you loved this video, please subscribe for more amazing content. This is Omni, signing off until our next great adventure.